Hey there. Every single second you're using your phone, there's this wild chemical reaction happening right in the palm of your hand. It's like this invisible engine powering our entire digital world. And today, we're going to crack it wide open.
I mean, think about it. We plug these things in every single day, use them till they're dead. But have you ever really stopped to wonder what's actually happening inside that little black rectangle? It feels so solid, right? Like it's just a block of something. But in reality, it's this crazy, dynamic, miniature chemical factory.
The best way to picture it? It's like a tiny baking soda volcano constantly erupting inside your phone. Seriously. And without that little volcano, our devices would be nothing more than expensive paperweights. So, if it is a volcano, what exactly is erupting? And where's all that stuff going?
All right, let's get into it. We're going to tackle the three big questions about your phone's battery. First up, how does it even work? How does it power your phone? Second, what's the deal when you plug it in to recharge? And third, the one that drives us all crazy, why does it eventually fade? Why can't it hold a charge like it used to?
Okay, so let's start with the battery when it's actually doing its job. When you're scrolling through social media, texting a friend, or binge watching a show. We can think of this as the outward journey, where these tiny, tiny particles are on a mission to bring your device to life.
So first things first, a super quick refresher on what electricity even is. It's just a flow of tiny, negatively charged particles called electrons. That's it. So in your phone, these little electrons are zipping from the battery's negative side through all the complicated circuits that make your screen glow and your speakers work, and they all end up at the positive side. The big question, though, is where do they come from in the first place?
Well, they come from lithium. It's called a lithium-ion battery for a reason, right? So the negative side of the battery, the technical term is the anode, that's where our whole story really kicks off. And it's made of graphite. Yep, pretty much the same stuff that's in your pencil. It's basically the perfect, super stable hotel for lithium atoms to hang out in.
And there's a fancy science word for this. It's called intercalation. All that means is that the lithium atoms are just neatly wedged between these flat layers of graphite. A good way to picture it is like sliding coins into one of those multi-layered piggy banks.
Okay, so here's the play-by-play. Lithium as an element has this one kind of weird property. It is desperate to give away its outermost electron. It just doesn't want it. So the moment you unlock your phone, a lithium atom basically checks out of that graphite hotel, but it leaves its electron behind. That little electron is now free, and it zips off through your phone's circuits, doing all the hard work. Meanwhile, the original atom, because it lost a negative electron, is now a positively charged lithium-ion. And this is so important. While the electron is taking the long, scenic route through the phone, the ion takes a shortcut right through a special liquid inside the battery itself.
So you've got the electron and the ion, both heading to the exact same place, the positive side of the battery, which we call the cathode. Now, this side is usually made of something like cobalt oxide. And here's the beautiful part. Just as much as lithium wants to give away an electron, the cobalt in this material is practically begging to gain one. It's a total chemical love story, a perfect match.
Okay, wait a second, let's pause here. If you have this constant stream of negative electrons flowing to the cathode, wouldn't that whole side just get super, super negative? And we all know that like charges repel, so wouldn't that just stop the whole process in its tracks?
And this is where the genius of the design really shines. That's exactly why those positive lithium ions are so critical. Remember that shortcut they take through the electrolyte liquid? Well, they travel straight to the cathode, and their positive charge perfectly cancels out the negative charge from all those incoming electrons. It keeps the whole system balanced, electrically neutral, and lets the reaction just keep on chugging along.
So there you have it. That's the story of how your battery discharges. By the end of the day, pretty much all the available lithium has made the trip from the anode over to the cathode, and your phone is dead. So what's next? Time to plug it in and send everybody back home.
Recharging is actually pretty simple once you understand the first part. It's just the whole process, but in reverse. Your wall charger basically acts like a really powerful pump. It uses the electricity from the outlet to literally force the electrons to leave the cobalt and go all the way back to the graphite anode. And what do the positive lithium ions do? Well, they're attracted to that growing negative charge, so they follow the electrons right back through the electrolyte, and they wedge themselves back into their little graphite hotel rooms, all ready for another day.
All right, so we've met the stars of the show, the anode, the cathode, and the electrolyte. But for this whole journey to happen safely and, not blow up in your pocket, there's a whole supporting cast of other parts, this kind of unseen machinery. So let's pop the hood and take a look.
Okay, probably the single most important safety feature is something called the separator. It's just a physical wall that keeps the anode and cathode from ever touching. Because if they did, Boom. Instant short circuit and probably a fire. Not good. Then you've got these collector foils that act like highways for the electrons, and a tiny little computer circuit that makes sure you don't overcharge the thing. All these layers are squished and folded together to save space. But, and this is super important, the whole process is never perfectly efficient. Every single time you charge and discharge, a little bit of lithium gets left behind.
And that little bit of inefficiency? That brings us to the final, and let's be honest, the most frustrating part of this whole story. Why does your battery's health, its maximum capacity, just seem to shrink over time? Why does that phone that used to last you all day now beg for a charger by 3 in the afternoon?
Well, allow me to introduce the two main villains of battery life. First, you get these unwanted side reactions. Sometimes lithium will react with the electrolyte liquid and form this layer of gunk. You can think of it like chemical plaque on your teeth. It permanently traps some of that precious lithium, taking it out of commission forever. And the second villain, this one's a big one, is letting your battery die completely. Draining it to 0% can cause permanent, irreversible damage on the cathode side. It creates these new compounds that basically lock away both the lithium and the cobalt, meaning there's just less stuff available to do the work. So, after all that chemistry, what's the one practical thing you can do? It's pretty simple, actually. To fight back against that second villain, just try your best not to let your battery die completely. The science is really clear on this. It's way healthier for the battery's long-term life if you plug it in when it gets down to, say, around 30 or 40%.
And really, that's the whole story of the volcano in your phone. But what's so cool is that even though the specific chemicals might be different in other batteries, this basic principle is always the same. You've got one material that's dying to give away electrons, another one that's dying to grab them, and a clever little internal highway for ions to travel on to keep the whole thing from going haywire. So, we've just cracked open one of the most common black boxes in our daily lives. Kind of makes you wonder, doesn't it? What other everyday gadgets are sitting around, hiding these incredible stories of science and engineering, just waiting for someone to take a peek inside? Something to think about. Thanks for joining me on this one.